Hello guys. So today we are going to be proving the intermediate value theorem, or I think it's also called Bolzano's theorem. And that's a theorem in real analysis, and it's a pretty important one. It basically states that a continuous function, from AB to R, assumes all real values between f of A and f of B. So, basically if we have, I just draw a small diagram over here. If we have any function, and here is A, so that this is f of A, and here's B, so that this is f of b. Well, then if we choose any y, let's say like a y here between f of a and f of b, then we know that there exists an x in the domain of the function such that f of x equals y. So basically, the function will will obtain every value on this interval. And basically, this kind of makes sense, and all we need to know is that the function is continuous. And that's kind of an interesting thing about the theorem. It doesn't need to be smooth, it doesn't need to be differentiable, it just needs to be continuous. And we're going to see that in a proof, that actually, really, all we need to do is create a smart algorithm, and then the only other thing we're going to need is that the function is continuous, which is kind of a nice thing about this proof. We really don't need a lot of other stuff to prove the theorem. But what we're actually going to be proving is like a different, it's the same theorem, it's just a different statement. It basically says if f of a, b to r is continuous, and if f of a times f of b is less than 0, which just means that, one of them has to be negative, our graph has to cross the x-axis. So f of a, this can be, this can be a, and this can be b. So, f of a, f of b, basically one of the values has to be negative so that the function crosses the x-axis. Well, in that case, there exists an x in ab such that f of x equals 0. And basically, these two theorems are the same thing, because if we define a function g of x equals f of x minus y, well then when f of x equals 0, g of x equals y. So, it's basically, it's the same statement, it's the same theorem, just with two different statements. We're actually going to prove this one. And now, how we're actually going to prove it? Well, first of all, we're going to need a second theorem to prove this theorem, which is called the Cantor theorem. The Cantor theorem. And basically what this theorem states is that if we have two real sequences, an and bn, which are both real sequences, well then if these sequences have the following three properties. So first of all, an is less than bn for every n is n. So an will always be less than bn, even when they go to infinity. Then an is increasing, so an is an increasing sequence, and bn is a decreasing sequence, and then the last property is that the limit as n goes to infinity of bn minus an has to equal 0. Well, if all these three properties are satisfied, then we know that there exists an x between these two sequences, so an and bn, even when it goes to infinity, such that the limit as n goes to infinity of an equals the limit as n goes to infinity of bn equals that x. So basically what we're saying is that the two sequences have the same limit. And that, that really makes sense. Imagine we have our number line here. Here we start with a0, here we start with b0, so an is an increasing sequence, so it'll always be increasing. Bn is a decreasing sequence, so it'll always be decreasing. And that means they have to eventually meet at a limit. If not, eventually an would just be bigger than bn. So they have to meet at a common limit, and at infinity, they will equal the same value. So obviously at infinity they can equal each other, but for every real number, the an has to be less than bn. So this theorem makes sense. We're not going to prove it, but I can make another video about proving this theorem. But we're going to need to use this theorem. And how are we actually going to use this theorem to prove our theorem? Well, it's actually a pretty clean method. This is the proof by the bisection algorithm. So what we're going to do, so let's say we have our function here, like this. This is our function. This can be our interval a. So this is a. So over here will be f of a, and then this can be our b. So this can be our b. I'll draw it under. So basically this where it crosses, I can continue the function. Where it crosses here, this will be f of b. Now basically, what we're going to try to do is construct an algorithm such that we make two sequences. So, this sequence, let's say it starts at a0 and the b sequence starts at b0. We're going to try to construct two sequences. The an sequence will be increasing until it reaches you know, the x-intercept, and Bn will be a sequence which is decreasing until, you know, it reaches the x-intercept. So eventually, you know, we're going to try to construct an algorithm such that they both have a limit over here. You know, An will always be decreasing, Bn will always be decreasing. They're going to meet at 0, and basically, you know, by the Cantor theorem, we're going to be able to say that, you know, the limit that these two sequences are approaching exists, and that limit is exactly here. And, you know, then we're also going to show that f of that limit has to equal 0. So, I mean, the most important part of this proof is how do we actually make an algorithm that, you know, gives us such sequences an and bn, such that, you know, one is increasing, one is decreasing, and they meet at 0. That's the heart of the proof. You know, if you understand that, then everything else is easy. So how are we going to make that algorithm actually? Well, I mean, the easiest way is to kind of just show it first. So and then I'll actually write it down. So basically, what we do, we have a0 and b0, and then for the first step, we pick the midpoint between a0 and b0. So we pick, let's say, the midpoint over here. Actually, I drew the function too close to the midpoint, so let's say the midpoint's here. So just so we're not like already on it, and this we're gonna call c1, and then we check what f of c1 is. So bang, what is f of c1? And now, if f of c1 is less than 0, then we disregard this half of the interval here, and we only focus on this part of the interval. So basically, how we're going to do that is we're going to update our an sequence. So, you know, our an sequence starts with a0, and then its first term is going to be c1. So, you know, this will basically be a1. So, you know, a1 we're going to find as c1, and our bn sequence is just gonna stay for now as only b0. So we updated our an sequence, so it got the c1 term, and now we only focus on this interval here, and now we do the exact same thing again. So we find the midpoint between you know, a1 and b0, which is going to be over here, and this we're going to call c2, and now again we check what f of c2 is, and now see, in this case we see that f of c2 is greater than 0, and if f of c2 is greater than 0, well, then I can change my color over here. Then we only focus on this part of the interval, because, you know, the 0 is in this part of the interval. So we only focus on this part, and now how we're going to do that is by updating our bn sequence such that a sequence starts with b0 and its second term is now c2. So, you know, we define c2 now equals b2. And now we do the exact same thing again. So we find the midpoint between c1 and c2, which is a1 and b1. We find the midpoint over here, this is c3. We do the same thing. We check what f of c3 is. We see that it's greater than 0, so what we do is update our b sequence again. So our b sequence is now b0, c2, c3. So c3 is now, you know, is now b3, and we find the an just, you know, stays the same, and now we find the midpoint between, now we, you know, I switch the color, now we find the midpoint between this interval 2, and then eventually, you know, this is going to converge to 0, and we see that we construct a sequence such that, you know, the an sequence will only be increasing because we're going to add a c to our an sequence only if it's between these values, and we're going to add a b to our bn sequence only if it's between these values. So we see that bn is always decreasing and an is always increasing, but, you know, we can also we can never like cross the actual intersection of the graph. So, you know, an will always be less than bn. So now how do we actually write this down formally? So we start with, you know, we define a0 as a and b0 equals b, and then we say that cn is the midpoint between the previous two intervals. So cn equals 1/2 of a n minus 1 plus b n minus 1. So cn, you know, is just the midpoint of the previous two values. And then we check, we say that we look at f of cn, and then, you know, we have the conditions. So if f of cn is greater than 0, well, then we say that an equals a n minus 1, so an doesn't change, but bn we update to cn. So, you know, we saw that over here. So if you know, if it was greater than 0, we updated our b sequence, but our a sequence stayed the same. And now, you know, the same thing if f of cn is less than 0, for example, like for our c1 value, well, then we update our an sequence. So an equals cn, and bn equals bn minus 1, so it just doesn't change. And then we have a third condition, which is, you know, is also important. If f of cn, I wrote two brackets. This is also important to mention. If f of cn equals 0, well then, our x will just be Cn. So, in case our interval hits the 0 perfectly, well then our algorithm is done and we found the 0. But, here we kind of assume that it's never actually going to hit it. It's just going to converge, slowly to it, but it's never actually going to hit the value. So now, how does this theorem, does this algorithm, this simple algorithm, it's kind of the most important thing you have to understand. So we really make sure you get that. But does this simple algorithm now allow us to use the Cantor theorem to prove that that a limit exists and that the limit is exactly here, and this will we'll call x dash or x bar. Well, let's see. So basically, we see by how the algorithm is constructed that an always has to be increasing and the bn always has to be decreasing, and we also see that an can never be bigger than bn. It's just not possible by how the algorithm is constructed. So the only thing we still have to show is that the limit as n goes to infinity of bn minus an equals 0. And how do we show that? Well, it's really easy too. Basically, we see that bn minus an, so the size of a new interval, bn minus an, just equals bn minus 1 minus an minus 1 over 2. So, the size of the new interval just equals half of the size of the previous interval. As we saw here, first we started with a0, b0, and then, the size of the new interval just equaled half of the first interval, and then we split the interval again, and then we split the interval again. So we just keep on splitting the interval. So the size of each new interval is just half of the size of the previous one. So basically, if we keep on doing that, the size of bn minus 1, an minus 1, the size of this interval is just half of the size of the previous interval. So we can continue doing this until we get to b minus a. So just b minus a over 2n, because we're going to divide this by 2n times. So bn minus an, the size of that interval, just equals the official, this is b0, a0, we just defined it as a and b. The size just equals b minus a over 2n. So now we can clearly see that the limit as n goes to infinity, 2 to the power of n goes to infinity, b minus a is a constant, so this goes to 0. So we show that the limit goes to 0, so now we satisfied all three properties, bang, bang, bang. So we can use the Cantor theorem, and basically, now we know that by Cantor, we can say that the limit as n goes to infinity of an equals the limit as n goes to infinity of bn equals x dash. So we show that a limit exists, and this is what we're going to call our limit. And now, another important part of the proof, here's where we actually use continuity, because for now we don't need any continuity. We just need to create a smart algorithm. But now, the next step, by continuity, we can say that the limit as n goes to infinity, we're going to start with an, of f of an equals f at that limit, which is always less than or equal to 0. Now, this is also an important part of the proof. You really have to understand that, because a lot is happening here. First of all, why do we need continuity? Well, for example, the limit is n goes to infinity of f of an. You can only switch, you can switch this thing for f of that limit only if the function is continuous. Because, for example, if we have an easy example, let's say a function is defined to always equal 1 when x is less than 0, but then when x equals 0, it jumps to 5, and then it always equals 5 when x is greater than 0. So here it's defined here. So this function, well, if we have a sequence which converges to 0 from below, so you have a sequence, it's gonna converge to 0. Then f of an of that sequence, f will always be equal to 1. Even as an gets infinitely close to 0, it will never actually equal 0. It will only equal 0 at infinity. So f of an will always be equal to 1. So the limit as n goes to infinity of f of n will just equal 1. But the value of f at the limit 0 will actually be equal to 5. So it's not equal at all. So the function, here we have to make sure that f of x acts the same way. So we have to make sure that the value that the function approaches as n goes to infinity also equals the value of f at that limit. And continuity ensures us that. And now, so how do we know this is always going to be less than or equal to 0? Well, because, we initially defined f of a to be less than 0 because, f of v was positive, f of a was negative, because 1 had to be negative. And then, we only added, with our condition of the statement, we only added cn to an if f of cn is less than 0. We only update our an terms if f of cn is less than 0. So that means for for every n, f of an will be less than or equal to 0. And because of how we defined our algorithm. And this is why, and due to continuity now, we also know that at infinity the function will act the same way. The function will act the same way as it is when it's approaching the limit. So we also know that at infinity the function will also be less than or equal to 0. And now we can say the same thing for bn. We can say the limit as n goes to infinity of f of bn equals f of that x value, but that's always greater than or equal to 0, because initially f of b was greater than 0, and we only add cn to our bn sequence if f of cn is greater than 0, which means and because it's continuous, f at that limit will act the same way as the function when it's approaching the limit, so it will also have to be greater than or equal to 0. So basically we now have two things. We say that f of x is less than or equal to 0, and f of x bar is so f of x is less than or equal to 0, and it's also greater than or equal to 0. So the only value that's possible, the only thing that's possible if we want both of these equalities to hold, is that f of x bar equals 0. So we showed it. It's kind of a pretty clean thing. By the way, by how we constructed our algorithm and by using continuity, we basically show that the only way that that these two equalities are satisfied is that if f of x bar equals 0. And that's basically the end of the proof. So we just ended the proof because we found an x bar such that, we started our theorem, we created an algorithm such that we show that for any function, that we know crosses the x-axis, we can construct an algorithm such that, an will be increasing, bn will be decreasing. So we basically show that there exists two sequences in the domain which have the same limit, and the limit will be here by the Cantor theorem. And because of how we defined f of, because f of a is negative and f of b is positive, or f of b could be positive, doesn't matter, but one of them has to be negative, and because of this, and because of how we defined our algorithm, we show that f of that limit has to exist, and f of that limit has to equal 0. So for any function, we can use this algorithm, and we can find the limit, and that limit has to be equal to 0. So we prove the statement, and yeah, that's the end of the proof. And by proving this thing, this statement, it's the same thing as proving the initial statement. Just we can just change the definition of the function. So with this, we prove the intermediate value theorem, or Bolzano's theorem. So basically, this is kind of another way of showing a completeness in R. Like this. With continuity, we know that the real number line has completeness. So, it takes every value, and if a function is continuous, then also if it's continuous on its domain, then also the range will have completeness. It's also going to take every value of the range. So continuity allows us to take completeness from the real number line and put it into the range of the function. And yeah, that's the end of the theorem. Thanks for watching, and yeah, see you next time.